literally a signal is a means of conveying some information, but in the context of systems we take the meaning of a signal to collectively indicate the various variables which describe the status of the system at any particular point in the system or at any particular point of time. As far as electrical networks are concerned, the variables or the signals that we deal with are the voltages and currents. It is the signals, as I mentioned earlier, which so to say give the breath of life to a system or a network, because in the absence of signals the network or the system is completely lifeless, and therefore an analysis of signals and a knowledge of the various kinds of signals that one comes across is important for us. And when we are dealing with the dynamics of systems and networks, the signals are functions of time. We would have naturally an infinite variety of such signals possible which are functions of time. However, a few special kinds of signals are important for us because of their simplicity, for one thing. Later on we will also argue that any composite signal, any general signal can be decomposed in terms of these elementary simple signals, and therefore a study of these signals is of the simple signals is important for us, and we will see, we will first of all review some of the signals which are familiar to us already and introduce new types of signals which will be found useful in our study. Let us now talk about some various types of signals, elementary signals that we are interested in. One, a DC signal. So f of t is a constant A, is independent of time, f of t. So nothing further need to be said about this, so we leave it at that. Then we have an AC signal. What we mean by that is a sinusoidal signal. So a general form of the sinusoid is f of t root a cos omega t plus theta. And the whole AC circuit analysis is based upon signals of this type, and you know the importance of sinusoids in circuit analysis, because this sinusoid has got a very distinctive property. This is the only periodic signal which retains its shape, which retains its general waveform under the linear operations of addition of two sine waves of the same frequency, subtraction of one sine wave from another, the same frequency of course. Differentiation of a sine wave will lead to another sine wave of the same frequency. Integration of a sinusoid will lead to another sinusoid of the same frequency. So under the linear operations of addition, subtraction, differentiation and integration, the sinusoid retains its character, the same wave shape is retained. No other periodic function has got this wonderful property. The result therefore is that if you have a whole system with sinusoidal sources of the same frequency distributed all over, then when a sinusoidal current passes through an inductor, it produces a voltage which is sinusoid of the same frequency. When a sinusoidal voltage is applied at a capacitor, it produces a current, a sinusoid of the same frequency. Therefore all these currents and voltages in the entire system, as for example in a power system where we have got different sources at the same frequency, all currents and voltages ideally in every point of the system are sinusoidal of the same frequency. If we did not have this wonderful property, then a sinusoidal current in an inductor will produce a non-sinusoidal, some kind of if you have a non-sinusoidal current in an inductor, you will have a waveform of the voltage which is completely different, and if you have all these different types of waveforms mingling with each other in a complicated system, you will certainly, it will drive one to insanity if one has to analyze this, because the waveforms are so unpredictable and so complex. So sinusoid has got a wonderful property, and it turns out, as I said, this is the only periodic signal which has got this kind of property. And we have phasor notations which deal with sinusoidal signals, analysis of systems driven by sinusoidal signals. So we know all about this from the AC circuit analysis, so we leave it at that, except to remark at this stage that this is really a very wonderful signal. Then we have the exponential signal. So the general form of an exponential signal would be f of t is a, I will put, say, okay, a as a complex number e to the power of st, where s is also could be in general complex. A and s are in general complex. Now mathematically, therefore, when you substitute a value of t here, because s is complex and the coefficient a is complex, you get a complex value for this. So this is a complex exponential signal. Now what about the dimensions of s? You know from your, maybe some of your earlier courses, that whenever you have a physical equation in which an exponent appears, the argument of the exponent, this exponential function, that is st, must be dimensionless. Similarly, sin omega t, whatever it is, that argument must be dimensionless. So st must be dimensionless, otherwise you can't match the dimensions on both sides of an equation. If st had a dimension, then e to the power of st has 1 plus st plus s square t square by 2 and so on and so forth. The dimensions of that you do not know what they are, because if it is st has a dimension of some x, some say m or l or whatever it is, you have m squared, l squared and so on. So because of these reasons, this must be dimensionless. If this is dimensionless, then the dimension of s must be something per second. st is dimensionless, therefore s must be something per second. And what is the quantity which is something per second? It is called frequency. Therefore we term this quantity s as a frequency, and because it is in general complex, we call this a complex frequency. So s is termed a complex frequency. It is not frequency in the sense something is repetitive in character like in a periodic function, but because its dimensions are something per second, therefore it is called frequency. This is called complex frequency. So this is the most general kind of exponential signal. Then if it is going to yield a complex value for f of t, what is the use for this? That is a question that naturally arises. As it turns out that whenever we have to deal with real systems, real signals, any complex signal of this type will always be matched by its mate, such that the sum of these two will always be yield a real term. For example, if I have a, for example, suppose is a complex number a e to the power of j phi, that is a complex number a, suppose I put it in this form, and e to the power of, say, s is equal to sigma plus j omega t, such a complex signal. This is the same signal I am writing for s sigma plus j omega, and for complex number a I am writing a e to the power of j phi, I have written this. This will always be matched by its counterpart, which will have the coefficient its conjugate, and likewise the complex frequency also will have its conjugate. Usually these two come together. So if you have a e to the power of st, you will also have a star e to the power of s conjugate t. These two will always occur together. So when you combine these two, you observe that you have a e to the power of sigma t and e to the power of j omega t plus phi and e to the power of minus j omega t minus phi. Therefore you will have 2a cos omega t. So, this is what this yields. So, this is a real signal. So, we do not have to be particularly alarmed about the fact that this is going to be yield a complex number, because we can be sure that in an analysis of any system that we are going to take up, this will always be matched by a conjugate quantity of the mate like this. So, the sum of these two will always be of this type. Now, depending upon the location of the complex frequency here in the complex plane, you have different kinds of behavior as far as the time dependence of the signal is concerned. Let me illustrate this here. So, the complex value of S can be represented in the complex plane like this, with x axis representing sigma and the y axis representing omega. So, suppose the S value of S is equal to minus 2, let us say a particular location, S is equal to minus 2. That means the value, the general value of S now takes a real value. This represents a signal which will be, say, a e to the power of minus 2t. So, you will have something like this. So, the time dependence of that, suppose let us take a to be a real number, because it does not have this is a real quantity, therefore, you cannot have a conjugate of this complex frequency, therefore, a has to be real. So, for example, a signal like this may be 3 e to the power of minus 2t. On the other hand, if I have, sorry, S is equal to 2, S is equal to sorry, I made a mistake here. If S is equal to 2 here, this represents an increasing signal like this. An example will be 3 e to the power of 2t. That means exponentially growing signal. If I take S is equal to minus 2, then this is an exponentially decreasing signal, maybe this is 3 e to the power of minus 2t. On the other hand, if I have two complex frequencies which are conjugates of each other like this, say this value equals minus 1 plus j2 and this is minus 1 minus j2, these two frequencies together, these two terms like this will give rise to a response which is of the form some m e to the power of minus t, minus sigma is now minus 1 cos 2t plus 1, something like this. So, that means you have a decaying sinusoid. That is how the quantity will vary with reference to time. On the other hand, if I have two conjugate complex frequencies with positive real parts, say 1 plus j2 and 1 minus j2, such two terms will yield a function of time which is m e to the power of t cos 2t plus p, and that would yield a time function which is growing in time, something like this. On the borderline between the left half plane and right half plane, suppose I have two frequencies, let us say j4 and minus j4. These two terms will yield a pure sinusoid and will have, say, typically m cos 4t plus theta. The m and theta or m and phi depending upon the coefficients, complex coefficients a that you are having. So, that means your complex frequency exponential signal like this encompasses in its generality a whole lot of time functions of this type. They can be a decaying exponential signal where S happens to be real and negative. It can be a growing exponential where S happens to be real and positive, and if S happens to be purely imaginary, a pair of such frequencies will give rise to a sinusoidal signal, pure sinusoidal signal, and on the other hand, if S having a negative real part, it indicates a decaying oscillations, and if S real part of S happens to be positive, think it has a increasing oscillations. So, we have this e to the power of S t has as a special case our sinusoidal signals. That means, sum of two such exponential functions will give rise to a pure sinusoid. So, we have taken now a look at three different kinds of signals which are namely the DC signal, the sinusoid, and an exponential signal e to the power of S t. And I mentioned that even though an exponential signal in general gives rise to a complex value for a real time t, but two such signals can combine and will give rise to a real function of time. So, the value at any point of time t will turn out to be real. We also have acquainted ourselves with the meaning of the term complex frequency. It is mainly because that particular coefficient of t in the exponential representation in the exponential signal has the dimensions of frequency. We call it a frequency. It does not necessarily mean that it gives rise to a periodic quantity, because none of these signals are purely periodic. All the characteristic of all these three signals that we have talked about so far is that they are smooth functions of time. That means, not only they do not have discontinuities, but you can take derivatives of these signals as they continue to have continuous, and therefore, this is a characteristic of these signals. So, in the next lecture, we will consider some examples bearing on these concepts, particularly the exponential signal and the complex frequencies, and we will also go on to discuss some signal waveforms which are not continuous, but which are important in our further study.